Okay, so if not, we want to start today, if possible, on the representation theory of SU2, which forms the backbone of all of representation theory. And we won't be able to go too much into representation theory, the explicit representations of the different groups, but I want to give you a little bit of flavor before we close the course. So today I want to tell you first about Schurs Lemma. So there are several lemma named after Schur, but this is the one that is useful for us. And this is, okay, so Schurs Lemma is if D of G is an irreducible representation, and that's something that you'll quite often find irrep as being the shortcut notation for saying irreducible representation, which is a mouthful. Say of a group G, and B is a matrix such that the commutator of B and D of G is 0 for all G in the group, then we can conclude that the matrix B is proportional to the identity matrix, okay? Okay, so this is kind of a very important theorem. So let me remind you what an irreducible representation is. So suppose that D of G, this set forms a representation of a group. This set forms a representation of a Lie group. I mean, this theorem is also valid for finite groups, but we are principally interested in Lie groups. So what does this mean? This means that forms a irreducible or an irreducible. So that means that there exists no matrix S such that the similarity transformation by S, leads D of G to have this form for all G. Okay. So this is the form that the matrix will take if it's a reducible matrix, and this can be 0 for compact groups. But if there exists no similarity transformation such that D can be put into this form for all G, then we say that collection, that set of matrices forms an irreducible representation of the Lie group. Okay? So all the defining representation that we have seen so far are irreducible representation. So let me give you an example of a reducible representation. Okay, so suppose that let's wait until we have done some SU2. Okay, so the proof of this theorem is pretty easy. I'm just debating whether I should, do you guys want to see the proof or just skip over to SU2? There are mathy people and there are physics people.
I'd like to see it.
Okay. All right, proof. So, so suppose, and without loss of generality, and you will see W log as a, mathematicians write without loss of generality. So without loss of generality, we can assume that B is a Hermitian matrix. And you might say, why? And that's because if you have a matrix B, which is not Hermitian, you can actually construct a Hermitian version of that, so to speak. Or you could construct a anti-Hermitian version of that. Okay, so if it's not Hermitian, we just work with this. Okay, so according to the statement of the theorem, B will commute with all D's. So that means B of D will equal to D of B for all G. So sorry, I should probably mention here that D has G dependence. Okay. Now, D is a representation, and we can assume D is a unitary representation, right? Okay, we can do that. So we can always construct, given a representation of a compact Lie group that is not unitary, we know how to construct a unitary representation where the matrices have the same dimensions. Okay. So now I'm not going to specify the G dependence explicitly. Now let's multiply both sides by D. So I left multiply by. So okay, let's start again. Sorry. So the equation I get is, so I write that equation. So if I take B of D, and that's equal to dB dagger, then I get D dagger B dagger is equal to B dagger D dagger. But D dagger is D inverse. And B is assumed to be Hermitian. So we get this equation. Now I left multiply by D and right multiply by D. So on the left side, I get this. On the right side, I get. Okay, so this is 1 and this is 1. So oh yeah, sorry. I made a mistake. Just 1 second. Yeah, sorry about that. So yeah, I made a mistake here. So let me tell you what I was trying to do. So what I was trying to do is that, of course, we have assumed that B commutes with D, right? But what I wanted to show is that B dagger also commutes with D dagger. B dagger also commutes with B, so D, so that when we take the when we take this sort of linear combination, this thing also commutes. Okay, so that's basically what I was trying to show. And of course, if I want to show that, then I cannot assume B is Hermitian. Okay. So there should be, yeah. Okay, so this goes then, B dagger of D is DB dagger. Okay, so what I've seen, sorry for the confusion, but what I wanted to show is that if BD is equals to DB, then B dagger D is also equals to DB dagger. And therefore, we can take B plus B dagger, which is, if B is not Hermitian, this is a Hermitian combination. This will also commute with D. Okay? Is that understandable? Okay, so now we can take B to be Hermitian. So because B is Hermitian, we know that Hermitian matrices can be diagonalized by a unitary transformation, right? So let's diagonalize B. So B, suppose there's a matrix, unitary matrix U, such that it diagonalizes B. Okay, so now we also do a transformation like that. Of course, this is diagonal, but that doesn't mean that this is diagonal. Now, let us write the equation B of D is equals to D of B in the basis in which B is diagonal, right? So B of D is a matrix. Let me write its matrix element. I is the row, J is the column. And that's equals to D of B. I is the row, J is the column. Now, there's a matrix multiplication here, but because B is remember that B is a diagonal matrix now, right? So the only non-zero component that B has are going to be of the form BII, and there is no sum over I. There's no sum over anything. So that this element of this matrix can actually be written as BII times DIJ. Okay, and these of course depend on G. And similarly here, this will be DI of J of G and then BJJ. And there is no sum here, okay? This is the most important bit. Okay? Now this is true for all G as well as I and J. And there is no sum, so we can just, get rid of these guys. And then what we'll have is that BII, of course, we're assuming that this is non-zero, right? We're assuming these are non-zero. If they're non-zero, well, this is the same, then BII is equals to BJJ, which means that the matrix B is proportional to the diagonal matrix, because all the eigenvalues are the same, right? Because these are the eigenvalues. Now, what if this was not non-zero, this was zero? What if the case where Dij of G is 0 for all G in G. So in that case, this is not a irreducible representation. This is not an irreducible representation, because if I write a matrix which is not an irreducible representation in the block diagonal form, and there is, suppose there is an irreducible representation here, there's another irreducible representation here, then if these are 0 for all G, then we are actually referring to these guys. Okay? So that means that if this was the case, then our initial assumption that we were dealing with an irreducible representation is no longer valid. So for irreducible representation, for all I and J and G, this is valid, means that these are non-zero. And that means that B is proportional to a diagonal matrix. So, for example, when you have a matrix which is a representation which is not irreducible like this one, the B matrix then will have this form. It'll have an identity matrix times some eigenvalue, and here it'll be 0, 0, and it'll be some other eigenvalue times some identity matrix, okay? But if you look at, this irreducible representation, although the B for the reducible representation is not the identity matrix, when you zoom into the bit which is the irreducible representation, for that bit, B is proportional to the identity matrix. Okay. Okay, any questions or comments?
Yeah, I didn't understand the part where Dij equals 0 implies that those blocks are 0.
Right. So the idea is, so the point about this equation is that this equation is true for all G, all I, and all J. Because it was, that was the assumption, right? This is true for all G. And I and J are arbitrary, right?
Yeah.
So essentially, if these are zeros for all of those things, then essentially it is not a reducible, it is not an irreducible representation.
Does that mean that D is just a 0 matrix?
Yes.
Okay.
Yeah. Okay, so Schurs Lemma has some nice, has a lot of implications. And one of them is that the unitary irreducible representations of finite and compact abelian groups are one-dimensional. Okay. So if all the matrices commute within themselves, as well as commute, as well as commute with B, then yeah, exactly. So, right. So comment number 1 is that the unitary irreducible representation of the finite or compact, Lie groups are one-dimensional. And why is that? Because this is because in that case, all the elements of the group commute. And therefore, they all have this form, right? So therefore, they are basically just specified by this one number, right? Okay. So that's comment number one. And you might say, okay, how about SO2? SO2 is obviously an abelian group, but we know that the matrices, the irreducible representation of the matrices of SU2 are not one-dimensional, they're two-dimensional. Okay. The caveat here is that these are not unitary representations. And if you allow the fields to be extended to complex numbers, then you can represent these matrices, you can diagonalize these matrices, and they will be given by two irreducible representations, which are one-dimensional. Okay. Okay, any questions so far?